Imagine receiving a completely clear mammogram and feeling a sense of relief. You've done your screening and everything looks fine. But a few months later, you feel a distinct lump. This is the reality of an interval cancer, a primary breast tumor diagnosed in the gap between routine screenings, often shortly after a negative result. These tumors are defined by their speed. Interval cancers consist of highly aggressive cells that multiply and spread much faster than a typical tumor, often appearing and becoming palpable in the window between fixed screening dates. A clear scan highlights a structural vulnerability in medical screening. Fixed human schedules often struggle to outpace this specific aggressive biology. The current standard of care in Europe relies on double reading. Every single mammogram is examined independently by 2 separate radiologists to minimize the chance of a missed finding. This system faces a massive logistical burden. Reviewing thousands of complex, low-contrast images leads to intense eye fatigue, a problem compounded by a global shortage of trained breast radiologists. The central challenge is finding these fast-moving tumors within a workforce that is already stretched to its physical limits. Catching these threats requires a workflow that filters out the routine background noise, allowing radiologists to prioritize the most subtle, high-risk anomalies. In Sweden, researchers launched the MASAI trial to test whether artificial intelligence could identify these cancers before they became interval cases. This study enrolled over 100,000 women and split them into 2 groups. Half received standard human double reading, while the other half were screened using a system supported by AI. The AI reviewed every scan, assigning a risk score from 1 to 10. Scores 1 through 9 went to a single radiologist. A 10 triggered a double reading by 2 doctors, with AI highlighting suspicious areas. This acted as an intelligent sorting mechanism, focusing the maximum amount of human expertise on the most dangerous images. The AI group successfully identified small, invasive, and dangerous tumors, catching them during the initial screening. As Table 4 shows, this earlier detection led to a direct result, a 12% drop in interval cancers appearing later. The number of these aggressive tumors fell from 93 in the control group to 82 in the AI group. The data suggests a targeted victory over aggressive biology. Researchers found fewer large, high-grade interval cancers rather than an overdiagnosis of harmless lumps. By integrating AI into the workflow, human doctors successfully narrowed the biological blind spot where interval cancers usually thrive. In screening medicine, there is usually a trade-off. Increasing sensitivity, your ability to find hidden disease, typically leads to lower specificity, meaning more false alarms for healthy patients. The MASAI trial avoided this trade-off. Screening sensitivity rose from 73.8% in the standard group to over 80% in the AI-supported group. While detection rose, the rate of false alarms remained exactly the same. Specificity held steady at 98.5% for both groups. This improved accuracy happened alongside a major logistical win. Because the AI handled the triage of low-risk cases, the workload for human radiologists dropped by 44%. This 44% reduction in workload shifts the focus of the screening room. By managing the routine data, the software allows human radiologists to devote their full expertise to identifying aggressive cancers before they have the chance to advance.